First of all, thank you very much to the organizers for putting this together and for the invitation. It's a pleasure to be here. So if any of you have run into my work before, you know I spend a lot of time talking about limit processes of beta ensembles, and this actually tends to involve a surprising amount of stochastic differential equations. And I didn't figure that topic would be too big of a hit in this crowd. I don't think most of you do stochastic differential equations. So I've chosen to spend a bit more time just telling you some of the backstory of where I work and some of the new stuff that's happening in my field that I think might be interesting to you guys. So we're going to start out with a very brief review of orthogonal polynomials on the unit circle. And just what it means when we talk about that in the case of just working with a matrix, or sort of a finite measure, or a measure with finite support. And then we can talk about how this fits into the beta ensemble picture, because you're not going to get away from that with me. And then we're going to talk a little bit about just how we can talk about counting functions in terms of random orthogonal polynomials. There's a very nice result from Killip that illustrates how they can be used very nicely. And then I'll tell you about sine beta, which is the beast that I usually work with, and a little bit about some results. And then if I have time, no promises, I'll tell you about some recent developments of using orthogonal polynomials and orthogonal polynomial recurrences and doing a direct relationship with Dirac operators that's been done recently by Valko and Virag. So let's start back at the beginning. So we have some sort of measure on the unit circle. And to any measure on the unit circle, we can associate a family of polynomials that is orthogonal with respect to this measure. And there's actually a bijection between measures on the unit circle and essentially families of orthogonal polynomials. And these families of orthogonal polynomials can be defined through something called their recurrence coefficients or their Vrblenski coefficients. So we have a bijection between measures. I have no idea what, this one. So there's a bijection between these measures here and these families of Vrblenski coefficients in the alpha k's. So what we're going to wind up studying is a lot of the alpha k's and the polynomials that they generate. And so one thing I want to point out is that if you have the case where mu is a finite measure, so for example, it's the spectral measure of a matrix, this whole story still works really well. In fact, in some respects, it works even better. And you can still have these alpha k's, except you only have n minus one of them if you have an n by n matrix. And you can actually build one final polynomial, which will just be the characteristic polynomial of the matrix. Okay, but let's just do the Szegö recursion for the second. So I said there's this family of orthogonal polynomials, and these alpha k's somehow can be used to build the orthogonal polynomials. So what do you do? So here's our family of orthogonal polynomials. To build this recurrence, we actually need one extra polynomial. So we're going to call this the reversed polynomial, or phi k star. So the way you get the phi k star, so I've written it this way. But what you should think of it doing is you just take the order of you take all of the coefficients of your polynomial and you just reverse the order, right? So the constant term now becomes the z to the k term and switch them all around. So if you do that, you can build the next term in your sequence by doing this recurrence, which we can code into matrix form this way. So one thing that sometimes, terminology that's sometimes used is you have this product of 2 by 2 matrices, and these are sometimes called transfer matrices. So I saw that name as part of a title of another talk. So this is your first step with transfer matrices this conference. Okay, so I mentioned on the first slide that one thing that can be very good to talk about is what happens if our measure has finite support. So for example, what if it is the spectral measure of an n by n matrix? So the spectral measure that I have in mind, this might not be something that you're totally familiar with. So a lot of times we'll talk about like the empirical distribution where you just put an equal weight on every eigenvalue. This one, it's still supported on the eigenvalues, but now your eigenvalues all have different weights. But we can define it this way, right? This makes a lot more sense for polynomials, but if you just apply your polynomial to your matrix, apply it to the vector E1, take the inner product with E1, this is the same as apply your function to the matrix and look at the 1, 1 entry, right? So as I mentioned, okay, you still have some sort of set of eigenvalues, so it's finite support, but now you have some extra coefficient qk that's called the spectral weight. And now we have a bijection, and it's an explicit bijection between these zk, qk, which we'll call the spectral data, and the alpha k over here, which would be the recurrence data or the Vrbonsky data. And just as a note, all of our alpha k's are in the disk if k is less than or equal to n minus 1, and then for n minus 1, the norm is equal to 1. And making the norm equal to 1 essentially truncates the sequence of orthogonal polynomials. You could then do something else after it. But these are all of the relevant ones, because if you have an n points on your measure, you can have at most n polynomials that are orthogonal with respect to that measure. And as I mentioned, okay, so we take these Vrbonsky coefficients and we generate phi0, phi1, and it turns out we have one extra one when we have this alpha n minus 1. And so we have phi n. Okay, so this is not actually orthogonal to the things that came before it, but the reason we like to talk about it is actually the characteristic polynomial of the matrix. So if, for example, you wanted to be talking about characteristic polynomials of random matrices, this might be one way that you can get at it, is through looking at this Vrbonsky recurrence. All right, so that was sort of your quick, rapid-fire introduction to orthogonal polynomials, a very curated selection of topics on orthogonal polynomials on the unit circle. So let's pull up our first random matrix model. So this should look familiar from earlier today or other talks you've been to. If you choose your matrix according to, just as a unitary matrix according to the Haar measure on the unitary group, or you could do the Haar measure on the orthogonal group, then you can you can write down an explicit joint density for the eigenvalues. And it's this one that I have written here. And then you just get this Vandermonde determinant to the power of beta. And this beta here, if we've chosen orthogonal, is 1, and if we've chosen unitary, it's 2. And the thing that you might not have seen before, or you might not have paid attention to before, is that if you look at that spectral measure that I was talking about, where you take the measure at E1, then you get this form. So your measure is this form, so it's got the same joint density as we had up here for the eigenvalues, and we have this extra spectral weight. And these spectral weights, they are independent from our eigenvalues, and they have a known distribution, which comes from the Dirichlet distribution. And then, because I study beta ensembles, I'll tell you that this whole picture holds for general beta. So even though there is still a bijection if you take this Dirichlet weight for your weights and this joint density for your eigenvalues, then you have a very nice bijection that lines up with the beta equals 1 and beta equals 2 case, where you can define your Vrbonsky coefficients in this way. So we take circular beta ensemble, we put in these Dirichlet weights, then the associated Vrbonsky coefficients are all going to be independent. This is another reason for moving over to the Vrbonsky coefficients, because independence is wonderful. And they are rotationally invariant, and this is the distribution of the norms. So we already said that at k equals n minus 1, we should have 1, but then the other ones have this beta random variable distribution. All right, so this is sort of the picture of what happens in the beta circular case. And let's see what I want to do with it. So what I really want to do with it is I want to start being able to talk about essentially a counting function for the eigenvalues. So you just do some linear algebra for a second. So this, remember, this was basically our characteristic polynomial. So we have a point is in the support if and only if this thing evaluates to 0. And then you can go back a step in the recurrence and you get this relationship. And then if you use some extra condition with the phi k star and you know that on the disk it's equal to this, you can go back and you can say, okay, now my e to the ix, this is in the support of my measure, if and only if the argument of this guy is twice the argument of phi n minus 1 minus x times n minus 2. And actually this right-hand side, this turns out to be a function that can be kind of useful more generally. So we're just going to define wkx to be twice the argument of phi k evaluated at e to the ix minus x times k minus 1. And if you do that, then per this argument up here, you take this omega and you subtract this argument and you divide it by 2 pi. This is actually going to give you the number of points in your spectrum that are between 0 and x. And you can check actually that this omega function is increasing. So this is just, I wanted to give you a picture of what's going on. This is a sample of what your omega function should look like. So one thing you should be thinking of is that we're essentially tracking, in some sense, the phase. Sometimes a related notion is the proof or phase of your orthogonal polynomial. It's not exactly the same thing I've defined here, but it's morally the same thing. So what you should think about happening is that we have some random polynomial, and this is what I want to emphasize here, is we have just defined these things as through some sort of random recurrence, right? You have some random variable, you define some polynomial, it looks kind of wild, but you'll notice that every peak and trough, you've gone across the 0 line. So you can define some sort of associated phase in here that will be monotone increasing, and it's going to look like this. It sort of snakes its way up. All right, so that's what our omega function looks like. So why is this useful? So I just wanted to give you one type of thing you can prove with this framework. So if you want to count the number of points in the n-point beta circular ensemble that lie between A and B, then Kilip showed that you get this central limit theorem for it. So if you want to know the Gaussian fluctuations of that, they happen on scale 1 over square root of log n. You have the centering and then some appropriate norming constant. And what's the idea behind that proof? Well, I mean, okay, he writes this a little differently, but it essentially comes down to the fact if you look at the change of these omega k's, and this, I want to emphasize, we can do this only for a fixed x, but if you only care a bit about this at a fixed point, then you can actually write this change like this. Here you would actually have omega alpha k bar times some other function of the previous orthogonal polynomial that's also norm 1, but because the alphas are rotationally invariant, you can just drop that piece. And so you really just get something that's basically another copy of alpha k. And so this omega n minus 1 minus nx, it's got this sum structure. It's basically got a martingale structure. It starts looking like it would lend itself to something like a martingale or standard CLT, and indeed it does. So you can prove this using the martingale central limit theorem, just from this structure of the counting function. All right. So this is, I hope, has convinced you that it's at least not completely useless to start thinking about these random orthogonal polynomials. We can actually prove some stuff with them. So another question that you might ask, and that I think we're all fairly familiar with, is what happens if you want to see the local interactions between eigenvalues? So at the moment, my eigenvalues, okay, I'm thinking of the phases of my eigenvalues in this picture. But I have n of them, and they're spaced out between minus pi and pi, and they all have spacing roughly 1 over n between them, right? At least order 1 over n. Well, 2 pi over n, but order 1 over n. And so in order to see some sort of limit, I would need to blow this picture up, right? If I want to see individual eigenvalues in the limit. So what do? I take my spectrum, and I center by x. By the way, I don't think I defined this anywhere, but I'm using this lambda n, the capital lambda n shorthand, to just denote the entire set of eigenvalues, or the entire set of points in beta circular, which I'm cheating and calling eigenvalues. So you take this and you subtract x, and you blow this whole picture up by n, and you ask what happens to it. Well, we're in the bulk, right? So we should get sign process behavior. We do get sign process behavior. There's no mystery here. And in fact, there's a couple things that make this whole problem a bit easier. You have rotational invariance all the way through the circular beta ensemble, and also for the Vrblinski coefficients. So we can always just zoom in near 0. And so if we want to say, hey, what does the local point process look like? Well, what can we do? We can take that counting function we were talking about, and we can look at, so this is just near 0, so we just need to look at x over n. This sort of means that we're looking at the interval that's 0 to x over n, and so if we scale that up, then we should see something that's just finite in the limit, right? Because that should accumulate sort of constant order number of points. And so this is the limit we're going to look a bit at. So this is a little confusing. So I told you, okay, we have these omega functions, and what's going on here is I have omega as a function of k, so this is in the index, and here it's as a function of theta, or the phase. So for example, if I go all the way out to the end here, this is omega n minus 1 going up. You should think about it as being sort of flat against the wall back there. And this would be how, if you were evaluating omega out at actually 2 pi, the way I've set this up, so if you were evaluating it out at 2 pi and you let instead the index of the omega change, you would see an increase there. So there's this roughly increasing surface in both directions. Just to give you a better picture of what's going on, here's a cross section. So if you increase in the theta direction or the x direction, this is a lot like the picture I showed you earlier where we had this smoothly increasing thing. But if you instead try and treat this index t, or the index k, as sort of a continuous function, so here what I've done is I've just plugged in a t and taken the floor. So if I do that, then I see something that's sort of rough. And it turns out that this will be the thing that gives us the sine beta description in the limit, is taking a limit of these things. And this is the limit statement. So if we let these x's have beta circular distribution, and I'm just sort of centering them around 0, then if you scale them up by n in the limit in distribution, they converge to sine beta. And for us, we're characterizing this through its counting function, right? Which is defined in terms of this crazy stochastic differential equation that I've put down here. Don't worry, I'm not going to do too much stochastic analysis here, but I'm going to show you a bunch of pictures. So we have this stochastic differential equation, and we let time run out to infinity, and we divide by 2 pi. So what you should think about is like, this picture here, this is going to converge to some sort of stochastic process that satisfies that stochastic differential equation, and you need to look at the end of time. That would be like looking at the n minus first omega. Yes. Sorry. It's twice the argument of your orthogonal polynomial minus x times k minus 1. It turns out to be the right quantity to look at for sort of counting the shift through the phase. Right, so we had this omega function, and really this omega is more naturally analogous to this alpha hat, which is just this alpha under a time change. And the only reason I'm going to tell you that is because I'm going to show you a picture of it on the next slide. So here's the omega. This time I've done n equals 500, and I'm evaluating at 10 over 500. So this would be like running it with x equals 10 and 14 over 500. So that's like x equals 14, or lambda whatever we're calling the variable at this point. And I've done the same thing over here, except that this is not the discrete picture. This is now running that alpha hat diffusion with the lambda values 10 and 14. And I just sort of want you to look at these and realize that they do exhibit fairly similar behavior. I mean, among other things, you'll see that the noise really dies down around multiples of 2 pi. That is something that happens. They both sort of roughly speaking go up. There's this extra rough piece at the end. This is sort of a proof by picture that they sort of have the same behavior. And you can make this convergence argument rigorous. This is essentially what Killip and Stoichkov did when they proved this limit, except that their diffusion ran the other direction in time, but it's basically the same thing. So this is how you see sine beta from this counting function. You really just try and figure out a description of that counting function that you can take a limit of, and that's what we do. And we do this in terms of the phase of the orthogonal polynomials. So you might ask, okay, well, you've done this and you have sine beta, and congratulations, you can now do this for all values of beta, but like, is this really like any use for me? I care about beta equals 2. And I would like to convince you that it does matter. So if you remember in beta equals 2, we have this beautiful determinantal point process version of, or description of this limiting process. And this description is great for some types of questions. If you want to ask, hey, what's the probability that I don't see any points in a really big interval? They can do this asymptotics like down to a t. Right? So these are a variety of authors who've worked on this problem, starting with getting various values of like, this exponent was originally undetermined and now it has been determined. And then now this constant term has been completely identified. I mean, they can do the asymptotics of this all day long and learn all sorts of things. If you want to do this for general beta, you don't do anywhere near as well. But for beta equals 2, I should have just put in the 2, but for beta equals 2, you can do these asymptotics. And for 1 and 4, you can also do these asymptotics extremely well. Okay, so this problem, okay, for beta equals 2, I grant you can do much better from the determinantal point process. But what about some of the other questions we want to ask? What if we want to talk about the number of points in a large interval? Well, there's the large gaps, that's what I just told you about. But what if I want to talk about large deviations? I expect to see roughly lambda over 2 pi many points in an interval of length lambda. So what's the probability that I see lambda times c many points where c is not 1 over 2 pi? This problem starts to be very hard in the determinantal framework because it's involving a rapidly growing number of points. So this is going to turn out to be some very hard Fredholm determinant analysis that I don't think was ever done rigorously. What if you just want to figure out the central limit theorem? I can give you a proof of the central limit theorem of the fluctuations around its mean in about half a page with the counting function framework, and it would be, again, a really difficult analysis problem to do it from the determinantal framework. So this is to just convince you that there are questions that we might care about that this description can be super useful for. So another one, basically any questions involving a lot of points, right? Because that's when the analysis gets hard for the determinants. Anytime you have a ton of points, the analysis gets hard. So what is the asymptotic probability of seeing k points in a finite interval if you take k to infinity? We can also address that. So a couple other things. So that's sort of like number of points in a large interval type questions. There's also this question that's interested from the physics side. So if you have, if we take beta to be this inverse temperature parameter, and you take beta to 0, you should expect to see something like a Poisson process in the limit. And indeed, you can get that. And then a result that was mentioned briefly earlier today that I'll tell you a little bit more is looking at the maximum deviation of the counting function from its norm. So this is one of these sort of log correlated processes. And we can say a bit about that as well. And finally, I want to mention a couple couple papers or a couple results that are on sine beta, and they don't really make use of this counting function structure, but there's other structures that have been very useful. So in particular, so these first 4 authors proved rigidity, and then something else that I'm not entirely familiar with. Chaibi and Najnudel also proved rigidity, and Leblay afterwards proved a central limit theorem for linear statistics of sine beta. I had everything else about sine beta up on the board. This is basically everything that's known. So I just wanted to make sure I highlighted those as well. So this is what we can do. I want to tell you a little bit about what we can do, or why we might be interested in something like the maximum deviation of the counting function from its norm. So sine beta, just like almost everything else as far as I can tell in the random matrix world, belongs to this class of processes that are sometimes called log correlated processes. So the really classical examples of these were some of the original branching processes. So branching random walk, branching Brownian motion. And then of course there's, if you have like a Gaussian field with log correlation, this is something that you're interested in. And one of the places that in random matrices that exhibits this same type of behavior are these characteristic polynomials of random matrices. And I just put a couple of the names of people who've worked in this area. It's a little bit more remote, but I wanted to also highlight, if you have a true log correlated Gaussian field, then there's a full convergence result, and I'll talk about what that means in a second, by Ding, Ryan, Zaituni, that leads to a very nice conjecture for sine beta. So here's the original conjecture for the circular beta ensemble. So, well, actually, for beta equals 2. So if you have a circular unitary ensemble, then if you look at the norm of its characteristic polynomial and you take the logarithm of that, you take the sup, and you do this centering, you subtract off log n minus 3/4 log n, this should converge to 1/2 k1 plus k2, where k1 and k2 are 2 independent Gumbel distributions. And again, so there's been some progress in this direction. So the first term, this was proved by Arguin, Bellius, and Bourgade. And for shortly after that, we had the second term by Paquette and Zaituni. And then for beta, all beta greater than 0, Chaibi, Manduel, and Najnudel proved not this convergence statement, but they proved that this object essentially to the left, that this thing was tight. So you don't get the distribution of the limiting random variable, but you get everything else. And why does this tie into our question? So back at the beginning, we had that this alpha hat was morally equal to this omega function, right? That was twice the argument at nt e to the I lambda over n plus t lambda. So if you wanted to look at the imaginary part of the logarithm, so rather than looking at the log of the norm, you just took the log of the characteristic polynomial and you looked at the imaginary part of that. It should have the same types of behavior. So if you look at the imaginary part of that, this should be comparable to looking at twice the counting function, basically the centered counting function times 2 pi, right? So this centered counting function is in exactly this family of questions where we ask what is the maximum of the characteristic polynomial over the set. So for sine beta, this is the natural question. I symmetrize the problem because it makes life a little easier, but you look at the number of points in the interval from minus lambda to the lambda, you subtract off its mean, and then there should be some normalization, C beta, so that when you subtract C beta times log x minus 3/4 log x, this converges. This is sort of the natural question. And we did basically the first step of it. So if you take the number of points in minus lambda to lambda and you center it and you divide by log x and you look at the maximum over all lambda between 0 and x, this converges to 2 over the square root of beta times pi in probability as x goes to infinity. So one thing I want you to know is that if you actually want to write down what this is, what happens is you wind up with essentially the martingale piece of the stochastic differential equation from the alpha diffusion. And so this winds up looking a lot like the situation where you have some sort of log correlated Gaussian field. So it's not exactly a Gaussian field because there's too much dependence of the alphas in here. But if you plugged in their expected value and chopped it off at an appropriate spot, because there is a reason to chop it off somewhere, if you did that and you applied the Zeitouni, Roy and Ding result, then this is the conjecture that you would get, that the maximum of this thing minus 2 over square root of beta. Sorry, this is off by, this should just be 4 over square root of beta times this log should converge to some random variable. And then it would be that this maximum minus 2 over square root of beta times log x minus 3/4 log x. That would then converge to some random variable. So that's the conjecture. Okay, so normally at this point in this talk, what I would do is I would try and tell you some more about how to prove this. But I decided I would rather do something else with the rest of my time here because there's sort of a lot of exciting things you can do still with random orthogonal polynomials, even random orthogonal polynomials on the unit circle. And you can tell this whole story on the line too. So let's go back to the Szegö recursion and see what else we can do with it. So this is our Szegö recursion that I mentioned before. And all I'm going to do is I'm going to take this TK matrix that I have up there, and I'm going to split it to a matrix that depends on the alphas, which is going to be A sub k, and a matrix that depends on the z, which is just going to be z, right? And I am going to do the following sort of change to my phis, or my orthogonal polynomials. I'm going to take a product of a bunch of these A matrices. I'm going to left multiply by the inverse of that product, and I'm going to do put in an extra rotation. And if you work out what happens is a recurrence to these fk's, if you do that, what you find is that fk plus 1 can be gotten from fk by just taking this matrix. By the way, so this is not for any z. This would be e to the I lambda, right? So this is only for phi k evaluated at e to the I lambda, so we're on the circle. But when you do it, you can write this as just this diagonal matrix being conjugated by this mk matrix here. Okay. We're going to step aside for a second. I want you to keep this in mind, and I'm going to put the next slide up, and then we'll come back and say why this is relevant. So the next slide is, let's let mu n be a measure that's supported on endpoints. Think of your spectral measure from your unitary ensemble, right? And we're going to define a matrix that's a time-dependent matrix, MT, that's going to be piecewise constant. And we're just going to put some extra scaling, Mn times T, in here. And we're going to let T go from 0 up to n over Mn. And we're going to consider the differential operator acting on functions going to C2 that's given this way. You just take tau of g is twice minus I, the diagonal with minus I and I, to the MT applied to g prime of t. And I'm going to stick in some boundary conditions. I want g of 0 to be parallel to 1, 1. So this is basically like g of 0 is parallel to my original orthogonal polynomials at 1, right? So phi 0 and phi 0 star are both 1. So that's actually what's going on here. And then my other boundary condition is I take what would have been essentially the boundary condition for my orthogonal polynomials, and then I have to do this transformation by the m in order to get my other boundary condition. it turns out that if you look at this differential operator, which is a continuous time differential operator, it's not a difference operator, its eigenvalues are all of the points where e to the I lambda over mn is in the support of mu n. So for example, if we took mn equal to n, and we started with our circular beta ensemble, and we constructed this tau, we take the limit of tau and we should get some sort of operator for sine beta. It's exactly the scale that it's happening at. But this is not the only setting you can do it. There's all sorts of random matrix models that you can put on the circle that we don't have operator limits for, that we might potentially be able to get operator limits for by using this. And that's what I get very excited about. So how can you see what's going on? So it's a differential equation, right? So we've got this set up, but on fixed time intervals, mn is just constant, right? So this now becomes a differential equation we can actually solve on those intervals, right? So if you go, sorry, this should be mn and mn. I missed a couple. That should be mn. This was stolen from something where these were all n to the 1/3, as you can tell. So these should all be mn, but if you do that and you say, hey, I want to solve what happens at time k plus 1 over mn, that's the same as just multiplying my solution at time k over mn by this matrix, because I can solve that differential equation. And then this should look familiar because this is exactly this, right? So it's exactly how you change the f's. So this was sort of, to me, a really exciting piece of machinery because I have lots of plans with it. But I was hoping that other people might also find this kind of inspiring because it gives you a really nice connection between the situation where you have a finite number, where you're doing, I mean, we always have this problem when going from the finite end to this continuous limit, and you go from difference operators to differential operators. So you have to prove some appropriate form of convergence, and you have to wonder, hey, do they act on the same space? I mean, I don't know if any of you guys have ever looked at the soft edge proof, but they do a lot of work to deal with the fact that all of the operators that they're working with, they live on different spaces. But here, if you do this, now you actually have an operator that lives on exactly the same space of functions as what your limiting operator would want to live on. And so your convergence issues, they get much easier. They get much, much easier to deal with.
So can you get the result of the soft edge for expected?
So the soft edge, I don't know, because you need to come up with a circular model that would come down like the square root right at 0. So you need to find an appropriate model for that. So with Maurice Dutz at KTH, I'm looking at a model where, so soft edge, right, is if you come down like a square root. And sometimes, so a bulk would be like if you were zooming in here. And you can also get models that come down like this and sort of just kiss the axis. And here, if you try to do a local point process limit, you should get something that's related to the Painlevé-2 equation. So this is where I'm currently focused. Maurice and I are trying to come up with an operator limit that works for this kind of situation.
Is that for a beta ensemble?
For a beta ensemble.
I see.
Yeah, exactly. But there's a bunch of other distributions that relate to having sort of merging cuts or various things like this that have not been done for the operator limit, right? The operator limit's been done for the bulk, the soft edge, and the hard edge. And so there's a lot of space, and I think a lot of nice interactions that could come from the interaction with the integrable systems community, because we've been a little bit siloed off and just working on sort of the basics. And that's why I really wanted to sort of share this picture, and there's a lot more in their paper, but that's really actually all I wanted to say today.
There's time for questions. So I had one.
Yes.
So if you take random orthogonal polynomials, but look at the polynomial of degree half, I mean half of the total
Right,
number of
n
numbers,
over 2 or something.
and
Yeah.
then let n grow, do you know anything about where the zeros of those things
No,
live?
actually, that's interesting. I was just wondering about questions related to this earlier today. So we should talk about it, but I have no idea. I mean, actually, in some sense, you do, because it should be. It should be essentially the same behavior as the n minus first polynomial. Should be, because nothing else has changed, right? I mean, okay, it should be the same behavior as the n minus first polynomial where you consider the ensemble that had like n over 2 number of points. Because none of the distributions of your alpha k's change, right, as you grow. So that behavior, in a sense, should be the same. You should still be able to say something about it.
Questions? So let's, wait.
Is there any chance of saying anything about kind of Fisher-Hartwig singularities or the analogs? So if you want like more details about the counting function through this last one instead of your previous kind of
right.
approach.
So Maurice and I looked at that at one point, and it seems like you could certainly, I mean, you can certainly get the asymptotics for the single point and maybe even multi-point, but you can't get anything precise. And apparently there's people who already have maybe figured out how to do this in full generality, so we sort of walked away from it. So we'll see what happens, but it looks like you can certainly do sort of the first order asymptotics that you would want in order to see Fisher-Hartwig for the jump singularity. Because the counting function really, it's set up much better for doing jump singularities rather than, it doesn't seem to play quite so well with the logarithmic singularities. It's good at jumps. Yeah.
So let's thank Diane.